Hello, welcome to this video. Today we're going to do this problem. So this problem was on the IMC of 2015. It's day 1, problem 1, and this is the problem. So let A and B be real matrices of size n by n. This is what this means. That satisfy A inverse plus B inverse is A plus B all inverse. Now, so I should mention, of course, A and B and A plus B are all inversible matrices. Show that the determinant of A is the determinant of B. And then a sort of second part of the question, is this true for A and B that have complex entries of size and are of size n by n? So let's begin. So let's look. So the defining thing for matrices is if you multiply them by the original matrix, you get the identity matrix. So what we're going to do here is multiply by A plus B on both sides. So we'll have A plus B times A inverse plus B inverse equals A plus B times A plus B inverse. Now this is the identity matrix, which I'll mark as I. But now let's look at this. I know this is equal to, okay, A times A inverse, which is the identity matrix, plus A times B inverse, plus B times A inverse, plus B times B inverse, which is again the identity matrix. And so we get A times B inverse plus B times A inverse is the negative of the identity matrix. Also, I just subtract just these two from both sides. So now what we're going to do is multiply by A on from the left. So by A from the left, so now I get A times B inverse times A. Now B times A inverse times A. A inverse times A will be the identity matrix, so B times the identity matrix is just B. And this is equal to negative I times A is just A. So now we get the negative of A minus, so minus A minus B is equal to A, B inverse A. Now this might look like something that you want to plug into here and try to play with it, but in my opinion, this is really something to try and look at it. Because let's try to think about it. Our original statement was symmetric about A and B. We flip A and B here, we get the same exact thing. But at the end, here we did something that's not symmetric. We multiplied by A and got this. So what if, because this is symmetric by A and B, if I flip A and B here, I know that negative A minus B will be the same as if I flip B and A here. Because if I flip A and B in the original statement, I would get the same statement. You can also think of it as just multiplying by B here instead of A. But anyhow, I'll know that if I flip B and A here, I'll get the same thing. So this is equal to B, A inverse times B. So now I'm going to focus on this equation. If I take the determinant of both sides, so the determinant is multiplicative, so the determinant of A, B inverse A, is just the determinant of A squared, because I have two A's, times the determinant of B inverse. Now the determinant of an inverse matrix is 1 over the determinant of the original matrix. So this is times the determinant of B, so negative 1. And this is equal to the same thing if we just flip them. So this is equal to the determinant of B squared times the determinant of A to the negative 1. Now, make this this little box here. Let me bring this up here. I multiply by the determinant of A and the determinant of B on both sides. I'll get that the determinant of A cubed is equal to the determinant of B cubed. And since A and B are both real matrices, their determinants are real numbers. So if I take the cube root on both sides, I'll get that the determinant of A equals the determinant of B, which is what we wanted to prove. So this is the first part done. Now, is this true for A and B, which are complex matrices? And so this is what I'm going to do. I'm going to pick two, I'm going to pick A and B to be 2 by 2 complex matrices, like so. A will be 1/2 plus root 3 over 2i times I2. I2 basically indicates this is the identity matrix of size 2 by 2. So this is what I'm going to pick A to be, and B I'm going to pick to be 1/2 minus root 3 over 2i times I2. These are two complex matrices, and the cool thing is, this matrix times this matrix, I'll let you check yourself. Well, not this, okay. This matrix times this matrix is exactly the identity matrix, or this number is exactly the inverse of this number. So if I do A inverse plus B inverse, this is like saying this is B plus A, because A inverse is B, and B inverse is A. A plus B, you'll notice, I'll have 1/2. 1/2 here that will turn to 1. Root 3 over 2 minus root 3 over 2 will be 0. So this in total will be the identity matrix. This, again, if I add A plus B, I'll get the identity matrix. The inverse of the identity matrix will be again the identity matrix. So we'll get I2 equals I2, which is indeed true, but yet the determinants of both of these is just this number squared, because they're of size 2 by 2. So the determinant of A would be this number squared. The complex number you get is -1/2 plus root 3 over 2 times I. And if we square this number, what you get is -1/2 minus root 3 over 2i. So these are different, yet this condition is satisfied. So for complex numbers, this is, so we solved this, the answer is no. And so we solved this part and this part, so we solved the entire thing. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be doing more interesting problems and things like this in the future. And finally, that's it.